today based on symmetry and closure. Now, we're going to start with real numbers A, B, and C. And a lot of you might prefer just to say that they can't be equal to 0. Okay. So we start with three real numbers that are not equal to 0, and that's what this means. This means the real numbers minus the singleton 0, set subtraction. And we're also given that the products of each pair are members of the rational numbers. Now, y'all, just a standard rational number looks like this. M and N are integers, and that's what we mean by rational number. Okay, let me make a Q there. Not sure why Q got accepted as the symbol for rational numbers. Now, we're supposed to show that given these three conditions, I guess, three products that are rational numbers, we're supposed to show that the sum of the squares of the individual rational numbers is a member of Q. And it's what it's going to do, y'all. This is going to be it's a symmetrical problem. So the closure, I'm going to use closure to save some work here, and the magical word similar. Okay, so closure. There's closure, and what I mean by that is if you add two rational numbers, or multiply two rational numbers, you get a rational number back, and we'll make use of that. Okay, the proof's fairly easy. I'm just going to prove that a squared is a member of Q, and then it will follow just symmetrically. You'll see after you see the proof why it immediately follows that b squared and c squared would also be rational. Okay, so we start out with taking the product of two of these guys, AB times AB. That makes sense. So we're trying to show a squared. But AB, this should be AB, sorry, this should be AB times AC right here, my bad. This should be AC, okay? Now, both of these numbers are posited to be rational numbers, so their product is rational. Also, a little bit of algebra tells you this. And so what we know is that this product a squared BC is equal to a rational number also. So what are we going to have right here? Let's see, a squared. Let me just write it. Let's just call it R, okay? We'll just call it R, a member of Q. Okay. Now, so you can see right here that a squared is going to be equal to BC, or it's going to equal to R over BC. Now, I should have mentioned division also. We'll use this symbol for division. When you divide two rational numbers, you get another rational number, right? So that's simple enough. It's a nice little proof, and essentially based on the closure properties of the rational numbers. And you can see why we didn't want them to be equal to 0, because you would have had to divide by 0 right here. So the real number not equal to 0 is necessary condition here. Okay, now also, as I said earlier, so we've showed that a squared is a member of Q, and I'll bail out and use this word similarly. Similarly, b squared and c squared are members of Q, right? Okay, now we'll use the addition probably. We've shown that a squared is a member of Q, and we've waved our hands and said similarly b squared and c squared is a member of Q, but this is very easy to see. Just the whole thing's symmetrical, really. It has symmetry. In fact, these objects summed together is what they call an elementary symmetric polynomial. Okay, if you want to explore that a little bit more. But again, so we've shown a squared is a member of Q, and by similarity argument, we know that b squared, c squared is a member of Q. So we can conclude that a squared plus b squared plus c squared is a member of Q, is a rational number if you want to go to the trouble to utter it. Okay? Okay? And it's QED time. Okay, y'all. Again, I liked it quite a bit. I think it's a fair usage of similar. It's just kind of a waste of time to go through the same thing when you know the same structure is going to happen. If you pick another pair, you'll prove that the other one is a rational number. That's just basically what's going on, and I just did it as a time saver. Okay. All right. Thanks for viewing.